record the session as well. So
thanks, Diane. Okay, it's 12 p.m. now, so let's get started. Hello, everyone, and welcome to the October Economic Outlook and Policy webinar series. Thank you for joining us today. My name is Seung-Ki Lee, and I will be your moderator for today's session. We have a fascinating topic prepared by Dr. Abdoul Sam. Let me briefly introduce today's speaker. My brilliant colleague, Dr. Sam, is a professor in the Department of Agricultural, Environmental, and Development Economics, AED, here at Ohio State. His research focuses on environmental economics, particularly in examining the determinants, effects, and effectiveness of voluntary pollution reduction programs, which have become an essential part of the environmental protection toolkit in the United States and many other countries. Today, Dr. Sam will discuss landfill gas and its role in U.S. energy production. With that, let me turn it over to Dr. Sam. Abdul, the floor is yours. You're muted.
Yes. Thank you so much, Seung-Ki, for the very kind introduction. Good afternoon, everybody who's online. It's a pleasure to be with you. Let me, before I get started, just acknowledge my co-author, Jung-Gun Park, who is also a PhD student in the program. In this paper, what we do is that we try to empirically evaluate one of many methane focused programs that are designed by the EPA over the past 30 years or so with the intent of reducing methane emissions. Particularly, we look at the landfill methane outreach program, which, as the name suggests, is geared towards reducing methane from landfills in the United States. This is a program that has been in existence for a while now. To our knowledge, nobody really has sought to evaluate its efficacy in achieving its primary objective, which is important because it is a voluntary program. And its primary objective being the capture and conversion of landfill gas into alternative energy sources. We also, in addition to that, try to understand or evaluate the extent to which this process of converting landfill gas into energy provides sort of positive environmental outcomes in the form of reduced greenhouse gas emissions. So you'll hear me talk a lot about acronyms, LMOP and LFGE. Just want to make sure that we understand what they are. I wish I didn't have to, and I'll try not to use them as much, but if I do, LMOP simply stands for Landfill Methane Outreach Program, and LFG stands for Landfill Gas to Energy. So that's what those two stand for. As I mentioned to Seung-Ki, if somebody has a question, feel free to, to ask a question along the way. You do not need to wait until the end. And if I'm not tracking the chat, Seung-Ki will help us track that chat function. So before we sort of get to the results, just a bit of a background about landfilling in the United States, as well as methane emissions and policies about those methane emissions. We, as Americans, produce a lot of waste, about 4.9 pounds of waste per person per day. That's about 290 million tons of waste per year, according to the EPA. So that's a lot of waste. As you can imagine, a significant amount of that is landfilled. About half of that ends up in landfills. About a third is recycled or composted. And about 12% ends up in waste to energy facilities where the waste is simply incinerated and converted into energy as well. Looking at the sort of composition of landfill waste, not surprising, food waste is the #1 source of landfill waste in the United States. About a quarter of the waste is related to food waste. And if you add up all of the sort of organic sources of waste, that's just over 51%. So that would be food, wood, paper and paperboard, and then your trimmings and so forth. So that's important. Why? Because as this organic waste decomposes in a landfill environment with the help of microorganisms called archaea, it produces as a byproduct landfill gas. And landfill gas is composed primarily of carbon dioxide and methane, with slightly more methane than carbon dioxide. But it also includes sort of non-negligible amounts of something called non-methane organic compounds. These are hazardous air pollutants like benzene and vinyl chloride, which have been linked to cancer and respiratory illnesses. So very serious air pollutants. How big a problem is this? Well, municipal solid waste in the United States is the third largest source of anthropogenic methane emissions. And that's estimated to about 100 million metric tons of CO2 equivalents in 2022 going into the atmosphere as a consequence of methane emissions. So here we have sort of a breakdown of the different sources of methane emissions into the country. You'll see that natural gas and petroleum systems are the number one source. About 32% of methane emissions emanate from those systems. Number two is enteric fermentation, 27%. That's basically methane produced as a byproduct of the digestive system of cows, well, not just cows, but ruminants in general. Again, with the help of archaea, and that methane is typically belched out. So it's a significant source of methane emissions. And the third largest source is that piece of the pie that's pulled out, as you can see, that's municipal solid land waste. And it's about 14% of total methane emissions in the country. You might ask yourself, well, why looking at the third largest or the third most important source of methane as opposed to the first or the second? Well, that has a lot to do with data availability. The EPA has a fairly nice data set at the landfill level about methane emissions and ELMO participation and so forth, which is really the reason why we're focusing on that. At the same time, it is not a negligible amount. I mean, 14% of methane emissions into the US, just to give you a sense of what that is, or, EPA to give us a sense of how much we're talking about here in terms of greenhouse gas emissions, that's roughly equivalent to 24 million gasoline-powered cars being driven for a year. So that's a lot of greenhouse gas emissions being made through municipal solid land waste. So, not surprisingly, methane has become an important source of concern for the international community, and this is reflected in a number of initiatives that have been put in place to reduce methane emissions. I just have a few here. At the international level, there is a global methane initiative, which was created back in 2004. And the goal was to promote technologies that capture and convert methane into energy on an international scale. And then there is a more recent program, the Global Methane Pledge, that was adopted as part of COP26. I believe it was in Glasgow. You have about 158 countries come together, basically make this pledge that they are going to reduce methane emissions on average by about 30% from 2020 to 2030. And then at the national level, we have a lot of programs that the EPA has put in place. Just key examples include AgStar. AgStar is very much similar to LMOP, the one that we're talking about today, but it is one that is geared towards reducing methane emissions from manure management, from manure management from large concentrated animal feedlot operations. There's also Natural Gas Star to reduce methane emissions from natural gas operations. CMOP, which stands for Coal Bed Methane Outreach Program, to reduce methane from coal extraction. And then we have LMOP, which is the subject of today's study, the Landfill Methane Outreach Program. The distinguishing factor for all these programs is that they're all voluntary. None of them is mandatory program. Companies or landfills choose to be part of this, or they choose not to be part of this. And if they choose to be part of these programs, it is really up to them how much or how well they want to perform. But these are not enforceable commitments that companies make, which is an interesting feature of these programs. Now, that changed a bit, like in 2022, as part of the passage of the Inflation Reduction Act. New authority was given to the EPA to regulate methane emissions in the form of a market mechanism, basically a tax. So starting this year, methane emissions are going to be taxed to the tune of $900 per metric ton. And that's going to escalate to about $1,500 a metric ton of emissions by 2026 and later. There are some carve-outs, based on size and so forth, but it's a change in policy that's noticeable. Of course, there are some, so that's sort of the stick approach, or stick component, if you will. There's also a carrot component in the form of significant financial and technical assistance to companies and landfills and organizations that emit methane, in about $1.36 billion in terms of incentives to reduce methane emissions. So why so much focus on methane? Well, because as I suspect most people here know, methane is a very potent greenhouse gas. It is far more effective at trapping heat into the atmosphere than CO2 is. A molecule of methane traps between 28 and 29 times as much heat into the atmosphere as a molecule of CO2, according to the Intergovernmental Panel on Climate Change, the IPCC. And scientists who've been looking at this more carefully have estimated that methane emissions are responsible for about 30% of the global warming that has taken place since the Industrial Revolution era. And so that is a significant chunk of the global warming that can be attributed to methane. So this is according to the International Energy Agency. Now, the good news about methane, if I can say that, is that it has a fairly brief atmospheric lifespan. It stays in the atmosphere for about 10 to 12 years before it turns into CO2 through a process called hydroxyl oxidation that basically converts it into CO2. And CO2 is far less potent, as we talked about, than methane is. So what that means is, and the reason why there's so much focus on methane is because of that. Like if you can reduce drastically methane emissions, that can provide sort of a more sort of rapid mitigation of the rate of global warming than say compared to CO2 because of how much damage it can do in its first 10 or 12 years, in its 10 or 12 years that it stays into the atmosphere. So there were regulations also put in place as part of, I talked about the Inflation Reduction Act having taxing methane, but there's also a regulation sort of akin to your sort of standard command and control approach to environmental protection under the Clean Air Act that requires that landfills of a certain capacity, specifically landfills that have a capacity of 2.5 million cubic meters of trash, 2.5 million cubic meters of trash, or of waste. And at the same time, emit non-methane organic compounds, that's those air pollutants that I talked about, like benzene and vinyl chloride, that emit NMOx or non-methane organic compounds greater than 34 metric tons a year, that they have to collect and control the landfill gas, because those NMOx or non-methane organic compounds they're part of the landfill gas. So under Clean Air Act regulations, landfills of a certain size have to install a landfill gas control and collection system. And basically it is a network of pipes, it's pipelines and extraction wells, so you can take out the methane that's underneath the landfill, collect it, and then sort of take it all to a central processing point where it is dealt with. How is it dealt with? Well, generally two ways. It can be flared. Flaring is basically the burning of that methane that's been collected. It looks like this. So you collect it and you just burn it. And burning it basically turns it into CO2. So instead of letting the methane escape into the atmosphere where it can do a lot more damage than CO2, just burn it and turn it into CO2. So that's one way to deal with it. But what the EPA really prefers is that rather than simply flaring, is that the landfill gas that has been collected, that it be converted into alternative energy sources. That's LFG projects, landfill gas to energy projects. Now that's a much more investment intensive, capital intensive process, human resources intensive process as well, because the landfill gas that's collected from those extraction wells and shipped into a central sort of processing place, that landfill gas is, it smells bad. It's very raw. It has a lot of impurities. It's got too much moisture. It's got, too much CO2. It's got volatile organic compounds and other impurities such as siloxanes. Those things have to be scrubbed. The moisture has to be removed. And then it has to be, that's what makes it ready to be used for electricity generation or renewable natural gas generation. And depending on which one you want to do, the investment requirements obviously vary as a function of whether it's an electricity project or renewable natural gas. So for electricity generation, the way it works is sort of fairly similar to the way that our car engines work. This is an example of what we call a reciprocating internal combustion engine. that converts landfill gas into electricity. And so very much similar to the way our car works. If you have a gasoline powered engine, it's based on the 4-stroke cycle, where you've got gasoline is mixed up with air to create a combustible mixture. That combustible mixture is then ignited with a spark plug. And you can see that sort of spark plugs, it ignites it and it creates, rotational energy, right? That rotational energy is what spins our wheels, makes our car go. In this particular case, that rotational energy is what spins a generator, right? So a generator is connected to the internal combustion engine, and spinning that generator is what produces the electricity, and that electricity is then put into the grid. So that's one action. Another action is to simply further process and clean up that landfill gas to make it sort of a pipeline grade conventional natural gas. Conventional natural gas has a significant content of methane. It's about 90% methane. Landfill gas has only about 50% methane. So you need to process it way further until you get to that 90% content of methane. And then once that's done, you can simply then feed it into the pipeline, and it can be used for vehicle fuel or for anything that conventional natural gas can be used for. The picture that you see here is that of a recent landfill gas plant. That's a plant that is converting landfill gas to renewable natural gas in Pittsburgh, in California. Very, very recently. I believe it was in September or so that it was open. So the point here is these are significant investments. This is a lot of money, right? It's the same as flaring. If you look at the composition of these projects in the United States, about 70% of the projects that convert landfill gas into energy are electricity generating projects. About 30% produce either landfill for direct use, because you can do that too. You can just minimally process the landfill gas so they can be used directly in boilers or kilns, etc. Or you can process it even further so that it becomes renewable natural gas. So that's about 30%. Often, if you just try to find the economic viability of these projects, they're not so viable. Fortunately for landfills and for firms that want to take advantage of this opportunity, there are a lot of incentives at the federal level, and in so many cases, the state level as well, that can render these projects actually positive, have a positive net present value if it's just profitable. For example, as part of the Inflation Reduction Act, the production tax credit for renewable natural energy just went up. It was 1.2, I believe. It went up to 1.5 cents per kilowatt hour. So it's not as much as the other sources of renewable energy, but it's still, again, an increase in that amount from what it was before. There's also an investment tax credit that is meant to offset up to 30% of the capital expense. I think you might have seen in the picture that I showed you. This is a significant amount of money that you have to put in. You have to invest in to be able to do that conversion process. And the investment tax credit can help offset some of that cost. And in many states, most states, in fact, have renewable portfolio standards that mandate that power companies have to source some of their electricity from renewable energy sources. And because landfill gas energy is considered renewable energy source, that's an incentive as well. And because companies or firms might have to buy renewable energy certificates, and you can be a supplier of those renewable energy certificates if you have landfill gas energy systems. And some states also have state level grants to further incentivize the take up of this technology. Now, interestingly though, landfill gas energy is not very efficient. According to the EPA, a landfill gas to energy project can capture 60 to 90% of methane. And in the process of doing that, it also destroys non-methane organic compounds. That's the reason why the companies are required to do this, so that it can destroy those very dangerous sort of hazardous air pollutants. Now, the problem is, okay, so if it is 60 to 90, that means 10 to 40% of that methane is escaping into the atmosphere, right? It's what we call runaway emissions, and this is actually the optimistic number. A lot of people would object to that. Would say that it's very hard to find a system that can capture up to 90% of methane. It's probably less than that. So we're talking about a non-negligible amount of methane really escaping into the atmosphere. So in 1994, the EPA launched LMOP with really two primary objectives. The first one was to offset the cost of compliance for regulated landfills. As we just talked about, landfills are required, landfills of a certain size are required to put in place a gas control and collection system. So you have to capture that landfill gas, make sure so the methane doesn't go up as much as you can. That's expensive, right? So that network of extraction wells you've got to put in place, and then capturing it in that's money. That's a lot of money. And so rather than just capturing and flaring, if that quantity of landfill gas captured that is sufficient to justify its conversion to electricity, alternative energy sources, that's a very meaningful way of offsetting the cost of compliance. So that's one of the objectives. The other objective was to encourage landfills that are exempt from control from those regulations under the Clean Air Act to also control and recover landfill gas. So what you see here is a sort of a snapshot of LMOP participation in the United States throughout the country as of September 2024. So the purple dots, circles, those are active current landfill gas to energy projects. And the green sort of squares or rectangles represent here, potential or fuel candidate landfills that have been identified by the EPA as sort of potentially viable to produce landfill gas to energy. So you can see that the leading state in terms of adapting this converting landfill gas to energy sources, that's California. They have 53 ongoing projects, and they have 33 that are deemed viable to generate electricity, to produce any alternative energy sources as well. And that could be renewable natural gas, that could be electricity, or could be also heat. The second is, I believe, Michigan. I was there just last week to make a presentation on this. 41 projects, current and 14 ongoing. I'm sorry, 14 candidate rather than 41 ongoing, 14 candidate. The state of Ohio, we are right here. So we are less reliant on this than many states in this part of the country. 13 ongoing, 15 candidate landfills. And if you zoom into to Ohio, here's what we see. So the white dots, these are landfills that have no current project. And the blue dots are the landfills that have an LFGE project that generates electricity, right? So that's what the blue ones that you see there. And it looks like somebody has a question. Does LMOP, I'm just reading a question here, does LMOP database also include biogas projects from farm digesters or from, no, it does not, as far as I know. It is really just for landfills. There is another project, a separate program called AgStar, and that one is the one that is geared towards farm digesters that you're referring to. And whether there's a data for that, I do not know. I know there has been some studies on that, so there's definitely data on that, but I don't know exactly what the source is. But I do know LMOP is mostly just for landfills. All right, so this is the state of Ohio, if you will. Now, just come back to this. In terms of energy generation, how much are we talking about here? So the total capacity of these 542 operational projects is about 1,100 megawatts of electricity production. And a megawatt is typically estimated to produce to sort of provide enough electricity for 800 to 1,000 homes. So we're talking about 1.1 million, sort of the upper end of the estimation, homes that are producing enough electricity is produced to power 1.1 million homes from landfill gas. That's what you see here. So it's a significant, and that's just existing projects. We're not talking about the 444 candidates that have an additional 843 megawatts of electricity potential, but have not been exploited yet. So in terms of research questions, or if you more specific research questions that you want to go after in this paper, with respect to the empirics, as I alluded at the beginning, we first want to know whether this program was effective in promoting LFGE project development. That was the number one goal of LMOP, was to incentivize and promote LFGE, excuse me, project development, right? The capture of landfill gas and its conversion into alternative energy sources. So we want to look at that. Why is that important? Well, because it is a voluntary program. A voluntary program means landfills can choose to be part of it, they can choose not to be part of it. Even if they choose to be part of it, nobody's going to force them to undertake an LFG project. They'll obviously do what makes sense for them to do. So it's an important empirical question. And this being a federal program that, for which, resources are devoted to, we believe it's a valuable exercise to engage in. And at the same time, we should also recognize that there's heterogeneity between these landfills. And that heterogeneity may manifest itself in how effective LMOP is as well in terms of incentivizing LFGE project development. So some landfills, some owners have lots of landfills, and they have experience collecting landfill gas even before LMOP existed, or before they participated in LMOP. And so for those types of owners that have sort of experience with the technology, knows kind of how it works, would you expect LMOP to have an impact on those for those owners or not? Or do you see, or are we going to see an impact for those owners once they join the LMOP? Are they going to be even more likely to adopt additional LFGE projects or not? We believe that landfills that have no experience, or owners that have no experience with the technology, have never done this before, are more likely to find that help that the EPA provides more beneficial, and therefore more likely to engage into LFGE development. And also we have some landfills that are regulated, others that are unregulated, and that's essentially based on size and capacity. We also probably have sort of the most stark difference, I think, is between private and public landfills. Private landfills are way bigger. They have twice the design capacity of public landfills on average. Public landfill owners have way more landfills than private landfill owners have a lot more landfills than public landfill owners. So we're talking about 10 to 2 on average, 10 landfills per private owner to 2 landfills per public owner. So that is a significant difference. And if I'm a private owner, that means if I adopt an LFG in a particular landfill, I can leverage that knowledge across my other landfills. I can move engineers around. So and the profit incentive is much larger for private landfills because they're eligible for some of the tax credits that we talked about in a way that private landfills are not, because they're tax exempt organizations. So we want to account for that heterogeneity and see sort of whether the effectiveness of LMOP in incentivizing LFG, or if you will, and gas to energy recovery, whether that varies according to those characteristics that I'm talking about here. And the second aspect of this research is to look at to what extent, if any, does LFG project development reduce methane emissions? That is a very important environmental objective. You would think that when a company puts in place a capture and conversion of gas into renewable energy, that the incentive is going to be to capture as much methane as possible, right? Because the more you capture, the more you convert, the more money you make. So we'll see if that's the case or not. So those are the 2 key research questions that we're after in terms of the empirics of the paper. So just briefly talk about theory of change. So why would we expect LMOP to have a positive effect on LFGE? In other words, why would we expect this federal program, the Landfill Methane Outreach Program, incentivize or to be an effective vehicle or mechanism that incentivizes the adoption of landfill gas capture and conversion into energy? It is a voluntary program, as mentioned. It is based on a cooperative partnership amongst various stakeholders. So that's not just landfill owners. Obviously, they are at the center of this, but you also have energy providers. We also have buyers of electricity. They all can be members of LMOP, or participants in LMOP, if you will. What does the program do for participants? So if you choose to be part of LMOP, according to the EPA, you have access to these benefits. What are these benefits? First, technical assistance. And this is potentially a significant plus because not all landfills are good candidates for electricity generation. There are certain conditions that have to be met. You have to have a certain depth You have to have the composition of the waste has to be taken into account as well. If you're not getting much organic waste, you're not going to get significant methane generation, so it's not going to be worth it. The amount of precipitation that you get, amount of rain that you get is important because that creates moisture, which makes methane generation easier to get. Whether it's open or is it closed. So there are a number of things, technical aspects that are very important. And depending on the landfill, they may not have the bandwidth, they may not have the manpower or the technical expertise to make those calls. They may not have people to actually do that, undertake those studies. And so having the EPA do that for you is a very significant amount of help. And at the same time, the EPA will also do an economic feasibility analysis to see whether this is an economically viable project or not, once you take into account all these grants that you might be eligible for. So that economic feasibility aspect and the technical assistance then combined are very, very important, especially for landfills that don't have a significant employee base that cannot devote like a lot of people to doing this work, and it's potentially a significant number of man hours to do this work. LMOB will also undertake energy market analysis, and they will also do an outreach to potential buyers. So if you produce this landfill gas energy, who's going to buy it, right? How much could you expect to sell it? Of course, that's dependent on prices are. So they'll do that kind of analysis for you, and they'll do an outreach to potential buyers. And this is especially important if you are in a state where there's a significant source or a significant source of electricity generation is required to come from renewable natural energy as part of renewable portfolio standards. That creates a bigger market for you and bigger incentives for you to engage in this. They help identify financing opportunities. They do not provide the financing, but they help identify financing opportunities for landfills that are participants, and they also provide networking opportunities for participants. So if I'm a landfill owner and I don't have experience in LFG recovery, but I'm interested in it, Sankey, on the other hand, has done it before and is an LMO participant that will put us together so I can learn from Sankey about what's efficient, what works, what doesn't work, what's the best way of doing things. And so last but not least, they also provide public recognition, or if you will, what we call green credentialing. And that's important, especially to private landfills, like, to be seen as an environmentally responsible actor. They give you an opportunity to kind of reveal your type. If you're the type of owner that cares about environmental stewardship or cares about renewable energy, this is a way for you to showcase that commitment, and they'll put you in touch with the media to promote your LFG projects and so forth. So there is a sort of a significant number of benefits that participants get as a consequence of their participation. And it looks like there is a stop sharing it. So question I thought in the chat. Our carbon credit marketers verifies, etc. Take part in FGE projects as interested. They can be part of, and I'll talk about that shortly. They can be ELMO participants. Take part in FGE projects as interested. Yeah, not FGE, but ELMO. They can be part of ELMO. And I think my next slide will talk about that. Great question. So, all right. So who are the participants? Maybe I don't have that slide. Sorry. So I'll just talk about it here. So the participants are not just landfills. So energy providers can be part of it. Buyers, energy buyers can be part of it. So there are 4 or 5 types of participants. So you have the landfills. They call them industry. You have community, that's carbon credits. Credits, as we mentioned, that could be local governments. You have endorsers, that could be environmental interest groups, and you have power companies. So you have a lot of anybody who's got a stake in who's interested in the energy market. Anybody can be part of ELMO, and the requirements differ. Based on what type of participants you are. If you are a state participant, the expectation is that you're going to review the laws at the state level and sort of make it easier, remove the barriers that make it harder for people to implement LFG projects. if you're an industry participant, like a private landfill, the goal is not just to make you undertake LFGE, but to also for you to help the EPA and others see the benefit of doing that by undertaking case studies and promoting, and I'll show you a slide later on where that's taking place, promoting LFGE recovery. And so there are different actors along the value chain, so a lot of people can participate. It's not just landfills. I believe there was about 1,021 participants, and more than 400 are not landfills. They are other state or other stakeholders that are part of the value chain. So this is gives you a sense of the trends over time in terms of LMOP participation in LFGE. Again, LMOP is just this federal program that is designed to incentivize people to engage into landfill gas to energy projects. It's voluntary. You can say, I'm going to be part of it, or I'm not going to be part of it. So the solid line that you see on top, this is LMOP participation over time. So it started in 1994, as I indicated, and it kind of, not the first, but the bigger participant was waste. So in 1995, we had participation of waste management. That's, one of the biggest private landfill owners in the country. And then kind of it went up a little bit over time. And until 2003, you had a big jump. That was when Republic Services came in. That's the other big landfill owner in the country. And you can see sort of the trend kept increasing, not at an accelerating pace. And you wouldn't expect that because the rate of landfills creation in the United States is a very, very small one. So it is a small increase, but it's a steady increase over time. It's kind of plateaued a little bit towards 2017 and beyond, you can see. And then the second line here, this is the LFGE. So this is the number of landfill gas to energy projects over time. And it's also follows a fairly similar trend, increasing over time, except there's a bit of an inflection point in 2015 and beyond. You can see it kind of goes down a little bit. Why? So we were curious about this. Why is this happening? So we see more and more projects are being activated, and starting in 2015, we see fewer and fewer, right? So actually there was a decline. One of the culprits could be, energy prices at the time. They were flat. So the outlook wasn't very good for energy prices. But we think a bigger problem here is just the economic outlook has changed because of a lot of policies at the state level, at the local level, about diverting organic waste from landfills, reducing food waste, and then whatever waste is generated, not making sure it doesn't end up in landfills, it's composted or going in different sources. And that changes, obviously, the economic outlook for these projects because the organic waste is a very important important factor into this. And so I think that's what might be going on. That said, this is not, there's a pickup of the trend again. It's not reflected here, but in more recent, at least anecdotal evidence suggests that more landfill gas energy projects are being constructed. I just read a few days ago that Vision RNG has secured $207 million in financing to create 2 landfill gas to renewable natural gas facilities in Ohio. I don't know exactly where, but and then there are others that are just coming out live very recently. So it looks like it's again picking up. So Sankey, how am I doing on time here? Should I budget some for final questions?
Yeah, you still have about 20 minutes left. So yeah.
All right, I'll keep that in mind. So in terms of the empirics or the data analysis, we have this landfill level panel data set, as I mentioned. So this is the LMOP database, which is publicly available. It's available online. Anybody can see it. On top of that, we also have, we combine that with fugitive methane emissions from the greenhouse gas reporting program. Unfortunately, we have a lot more data from LMOP than we have from the greenhouse gas reporting program. So because our fugitive methane emissions come from the greenhouse gas reporting program, we are somewhat constrained in terms of how far back we can go. We can only go as far back as 2010, unfortunately, to track emissions and how they are related to LFGE and LMOP participation. Of course, landfills will not undertake a landfill gas to energy project just because they participate in LMOP, right? LMOP is an incentive, but it's probably not even the most important factor in why landfills would do this, right? The economics first have to make sense. So here in our analysis, we make sure that those factors are taken into account. So what factors? So the landfill level, the age of the landfill is important because it's the proxy for the depth of it, like how much trash has been accumulated, because that's important for the generation of landfill gas, whether it is open or closed. If it is open, that means it's still taking in waste, and so therefore it's going to be producing methane for a lot longer period of time. We look at precipitation and temperature because that's important for generation of methane. We look at GDP, how many people, population and GDP, that we believe those might play a role, because if you've got a rich county, for example, maybe there'll be more, they'll be diverting the waste away from landfills and more into composting, and actually reduce organic waste at the same time. We also look at, obviously, electricity prices and natural gas prices. We look at how much renewable energy demand there is to meet the renewable portfolio standards at the state level. So putting all of that stuff in an econometric model, we can estimate the effects of LMOP on LFGE. So this is sort of putting our estimates in a graph here. I can show a table as well. We start first by not accounting for these variables. Like, let's ignore these variables completely. Let's just look at LMOP and LFGE totally. If you're LMOP participant, how much does it increase the probability that you are going to adopt an LFGE project? Ignoring for now all these factors that I just talked about, the economic variables and the technical variables that are important for the methane generation. And then what we found here, so this is on the y-axis, we have the probability of adopting a landfill gas to energy project. That's what we have on the y-axis. And then here on the x-axis, we just have the time since a landfill has joined the LMOP program, right? So 0 is, that's when they first join, okay? -4 is, that means it's 4 years before they join the program, 3 years before they join the program, 2 years before, 1 year before, etc. So this is before joining LMOP. This is after joining LMOP. You wouldn't expect, before joining LMOP, we shouldn't see any difference between LMOP participant landfills and non-LMOP participant landfills, right? So even if I subsequently end up participating, before I participate, there shouldn't be any difference in behavior between me and another landfill that did not participate, right? Because I haven't participated. I will eventually later on, but I haven't yet participated. So that shouldn't make a difference. And so that's what we see here. So these diamonds that you see represents the change in the probability, or if you will, the difference in the probability of adopting an LFGE between LMOP participants and non-LMOP participants. It's off of 0. You can see it's in positive territory here. Is in positive, slightly positive territory here. But we also have these vertical lines. These are our standard errors, or if you will, our confidence intervals. Because this is a statistical model, we only can have estimates, not exact points. So these are point estimates. And so this is just to account for the sampling variability. How confident are we that this number that we provide here is different from 0? So because that vertical line here crosses the 0 point, or the 0 horizontal line, because we're crossing that, we are not confident that these point estimates are different from 0. And nor should we, right? Like, shouldn't be happening, because we haven't yet participated. And you can see there's nothing is happening. All these lines are intersecting with the 0. This -1, this is normalized to 0. This is right before we participate, right? So nothing is going on. Let's see after we participate what happens. So and so once we participate, you start to see things happening, right? Once you participate, you start to see that the probability of LFG adoption, which is what we have in the y-axis, starts to be bigger for LMOP participants compared to non-LMOP participants. This is the difference between those two probabilities. So it starts to hover into positive territory. And you can see that these bars, these vertical lines, none of them is touching this 0 line over here, the horizontal line. That means we have confidence. We have 95% confident that these estimates are actually not equal to 0, that these changes in probability are actually significant. There is a significant difference between LMOP participants and non-LMOP participants. How much we're talking about, I have here at the top of the slide, 7 percentage points. That the difference between LMOP participants and non-LMOP participants, when it comes to the likelihood of adopting a landfill gas to energy project, is 7 percentage points. Now, what does that mean in the grand scheme of things? Well, you have to first understand what is the baseline probability, right? For non-LMOP participants, the likelihood of adopting an LFG project is only 14%. So now you're adding 7% on top of the 14. So that's a 50% increase relative to the baseline probability. So that's a pretty big number. We have it also in sort of table format, if it is easier. This is before. Pre-treatment just means pre-LMOP participation, so nothing is happening on average. Post-treatment, once you join LMOP, the average after you join LMOP, the average increase in the probability of adapting an LFGE is 7 percentage points. And that can be broken down. You can see, so post is after you participate. This is the first year, it is significant, but at the 10% level. But we are much more confident about what happens after year 1, year 2, year 3, year 4. You see and see that these numbers keep going up, right? And next, what we do is we account for these controls because it's very, very important to account for these variables here: electricity prices, natural gas prices, precipitation, etc. And they might actually, if you don't account for them, you might get a misleading picture of how much LMOP is affecting LFGE. And sure enough, we do. Once you account for those variables, what you see is that the difference between the likelihood of LFG adaptation between LMOP participants and non-LMOP participants is significantly reduced. It goes from 7 percentage points to just 4 percentage points. I'm saying just 4 because it is a significant drop, but it is still a significant difference. So these are fairly abstract numbers. So what is it that we're talking about? During our sample, let me put it this way. For the sample that we have, which runs from 2010 to 2021, we had on average 645 LMOP participants. 645 LMOP participants, each one of them being 4% percentage points more likely to adapt LFGE. 0.04 times 645 gives you an additional 26 LFGE projects, right? That's what the number you see here. This is a big number because there is another study by Shanjian Li and others from Cornell that looked at a different angle, looking at how much renewable portfolio standards incentivize LFGE development. And they found 17 projects can be credited to renewable portfolio standards in their tax credit, in the investment tax credit. What we're saying here is that LMOP alone can be credited with 26 additional LFGE projects, landfill gas capture and conversion into alternative energy sources, which is not trivial. And obviously that there's heterogeneity there. These effects, indicated earlier, these effects are a bit different depending on whether the owners of the landfill have some experience capturing gas before or no experience at all. So if you have some familiarity with the technology, again, pre-trends before participation, you shouldn't see anything happening. And sure enough, these very large confidence intervals that cross the zero line tell us nothing is happening. But you can see that between those that have experience and those that don't have experience, you can see a divergence. Those landfills that have experience capturing gas before, participating in LMOP does nothing for it. Right? You can see that those bars are still crossing the zero line. There's no statistically significant effect. But if you look at the ones that have no experience collecting landfill gas before, that's when you see the benefits of LMOP participation. You can see that, that's the solid dark squares. You can see that they're all above the zero line, and the numbers, we're talking about 38% increase in the probability of adapting the FGE. And the number is even more stark when you look at public versus private. And you'll see that really what's driving this effect, this positive effect of LMOP, is really public landfills, not private landfills. Again, nothing is happening before people participate, but once they participate, you can see the difference between public and private. So the diamonds, that's the public landfills, you can see that it's just rising. The difference between that the LMOP makes in terms of incentivizing LFG adoption for public landfills keeps growing. It just goes up and up and up. Now, on average, we're talking about 100% increase in the probability of adopting an LFG. So it's just doubling of the odds that you're going to adopt LFG. If you are a public company that didn't join LMOP, and now that you join LMOP, you are significantly more likely to have an LFG project, as indicated here. We don't see anything significant for private landfills. You can see those bars, they all cross zero, telling us that there is no statistically different effect. The effect is not statistically different from zero, if you will. So that was That's really interesting. Is it because just government agencies listening to other government agencies? Or it could be just because private landfills have the economic incentives. They don't need anybody to incentivize them any further. And they have the know-how, they have the bandwidth, they have, they're much, much, much bigger. As I said, those scale economies are going to be beneficial, where you can, or learning economies maybe a better word, where you can kind of shift resources from one place to another, and then that can incentivize additional adoption without even being part of EPOM. Now, our final research question was about whether capturing landfill gas or having a landfill gas to energy project is going to have a positive effect on fugitive methane emissions. Fugitive methane emissions are simply runaway methane emissions from landfills. Methane is light, it's lighter than air, is going to rise up. And of course, the technology is very, very hard to put in place a technology or pipes to capture everything. Some of it is going to go up. Of course, there are some things you can do in terms of the covers, but capture of methane is very hard to have 100% of it. What we see is that having an LFGE really doesn't have any effect on fugitive methane emissions. So here, our y-axis is fugitive methane emissions in millions of metric tons of CO2 equivalents, right here. And here we have whether or not you have an LFG project and when did you start it. So before you started, again, these bars are crossing zero, nothing happening. Once you start, we don't see anything either. There's no evidence that having a landfill gas energy project is going to reduce fugitive methane emissions, which is really interesting. But when you think about it, it's not. It's a plausible scenario. Why? Because the EPA already requires that landfills of a certain size have to have a gas collection and control system, independent of whether you want to do an LFG or not. You have to capture the gas. You can flare it, or you can do LFG, but you have to capture it. And that is a precondition to having an LFGE. It's really that's responsible for reducing methane emissions, not LFG in and of itself. That's not fine. If you have an LFG on top of capturing the landfill gas, then obviously you have every incentive to capture as much methane as possible, because if you don't, it's like dollar bills escaping into the atmosphere, right? You can do that by trying to enhance the efficiency of your gas control and collection system, or what they do is you can dig additional extraction wells to capture more gas, or in some cases, landfills would recirculate leachate. Leachate is essentially any liquid that comes into contact with the waste. It has to be collected so it doesn't contaminate the groundwater. And then what landfills in some cases would do is that they will put it right back into the landfill to increase the moisture, right? Environmental activists don't like it, because when you increase the moisture, you increase gas generation. The problem is you don't capture 100% of it. A significant amount of it actually is going to go up. So it's not actually impossible that having an LFGE would result in increased fugitive methane emissions. We don't see that in our data, but it is conceivable that would happen. But again, we don't see that in the data that we have. But theoretically, it's possible. What we have done then, we say, okay, let's look at this just more carefully. So we looked at all the landfills that have a gas control and collection system. That's what this GCCS stands for, gas control and collection system. This is a requirement by the EPA for landfills of certain size. We look at those landfills, and then we try to see if there is a correlation between having that and fugitive methane emissions. And we get rid of all the, in this case, we remove all the landfills that have an LFGE, so that we can just cleanly see whether this is because of GCCS or not. And then what we see is that, again, here we don't intend to make a causal argument, just looking at a correlation. What we see is that landfills that have a gas collection system, they have fewer emissions. You can see this number is below zero. So this is the negative area here. So this is the percentage reduction in methane emission, in fugitive methane emissions. That's what it is. It's about a 24% reduction in fugitive methane emissions once you have a gas control and collection system. But again, it could be larger than this, as we're not trying to make a causal claim here. And then, then what we do is that we look at landfills that have a collection system in place, and then we see, okay, amongst those that have a gas control and collection system, let's see what happens when some of them have an LFG and others don't. How would their performance differ? Like, how does having an LFGE on top of having GCCS, does that matter for fugitive emissions? And again, you find it doesn't really. There's nothing significant here. Everything here crosses the zero line. All these bars are crossing the zero line, telling us there is nothing that is statistically different from zero. So in a nutshell, these LFG projects really, they don't provide any positive environmental benefits when it comes to the emissions of fugitive methane, when it comes to runaway methane. It really doesn't reduce that based on our data that we have. Now, this doesn't mean that these projects, these energy projects are, nothing for the environment. No, it doesn't say that. It doesn't mean that at all. In fact, they generate significant benefits to the environment in a different way by displacing fossil fuel energy generation, right? There's a displacement effect. If you are generating energy from landfills, that means you don't need to generate energy from fossil fuels. And landfill CO2, by the way, maybe I didn't mention that. Landfill CO2 is considered carbon neutral because that CO2 that's released from landfills, it is CO2 that was sort of part of recently living biomass. It was in plants, for example, that decayed. And that CO2 wouldn't be released whether they decayed in a landfill or whether they decayed outside of landfill. So it all goes back to sort of this natural carbon cycle related to photosynthesis, where plants capture CO2 from the atmosphere because they need it for their own metabolism. They eventually make way into into the food chain. They'll die or decay. That CO2 is released. It goes back. It will be absorbed again. So it is considered to be carbon neutral. So when you make energy from landfill methane, you are displacing energy that otherwise would be made from fossil fuels, just coal or natural gas. And the EPA has divided the country into 14 electricity regions. And for each landfill, they estimate how much, not for each landfill, I'm sorry, for each landfill gas to energy project, they have an estimate of how much avoided carbon emissions are resulting from that project. Okay, how much carbon is being avoided because of the displacement effect, because of the offsetting of fossil fuel energy. And obviously that varies, right? California is much more reliant on renewable natural energy sources than, say, Ohio. Ohio has a lot more on natural gas and coal. So if you have landfill gas in Ohio, the displacement effect is going to be much, much larger than what it would be in California, for example. And so based on that, we can estimate, the avoided economic damages, or if we avoid the social cost of carbon that we can attribute to LFGE because of this displacement effect. And so we created a table here. I don't know how much time we have. See, I'm going to skip the table but the slides are going to be available to everybody. But just to give you a sense, if you look at the LFG projects, right, depending on what estimate of the social cost of carbon that we take, we're talking about avoided economic damages between $1.4 billion and $4.7 billion because of landfill gas to energy projects for the whole United States, right? Yeah. A small fraction of that can be attributed to LMOP, but really the more important thing is to look at the whole picture. LMOP, because it's responsible based on our estimates of 26 additional projects, we're talking about avoided economic damages to the tune of $86 to $288 million. It's a wide estimate because the social cost of carbon is a pretty controversial sort of estimate, if you will. And so these discount factors reflect that. And so I have additional messaging, but I think in the interest of time, I'll skip that and just sort of give my concluding remarks. So what we find in this case is that this federal program indeed has had a positive effect in terms of promoting and incentivizing LFG adoption, LFG project development. We're talking about an additional 26 projects or so. We also find that even though LFG projects do not reduce fugitive emissions or runaway methane emissions, they do have a positive effect on carbon emissions or greenhouse gas emissions because they displace fossil fuel use, right? They offset the use of carbon of fossil CO2 rather. There are other benefits that I didn't talk about. Obviously, the proceeds from the sale of energy. Local job creation, because having these projects, you have to hire people locally to do a lot of that work. Unfortunately, sometimes at the cost of some other place, but locally, if you think about regions, that can be beneficial. I want to make sure that clarify what we don't want to imply here by this paper. We do not mean to imply that voluntary programs or LFG projects are the best ways to reduce methane emissions from landfills. That's not what we're saying. In fact, the better way to deal with this is to reduce, reuse, and recycle. And reduce how much waste you generate, reuse when you can, and recycle when you can. That said, the United States has a lot of land. Unlike, for example, Europe, or Asia, where there's a lot of focus more on burning the trash. And this landfilling is a huge business in this country. We have these landfills, they're producing a ton of methane, a lot of methane, and that methane, rather than letting it escape into the atmosphere, where it can do a lot of harm, this is a good way to deal with that. Having these LFG projects is a good way to deal with the methane that we currently have. While at the same time we're thinking about better sources or better ways to deal with it. But in the short term, it's an effective way to deal with this waste. And the EPA, I mentioned earlier, this is not something that has been forgotten about. This is still going. So I was looking at the EPA website. They have a webinar coming up on November 12th where they will be talking about hosting the host of the webinar is going to be, I think, 2 new LFG projects that were put in place very recently in Texas and New York. And I mentioned the new ones that could be coming to Ohio very soon based on Yahoo Finance. Like I said, Vision RNG claims to have secured funding, hundreds of millions of dollars to do this in Ohio as well. I will stop at this point, and if there are any questions, I'm happy to take.
Wonderful. Thank you, Abdul, for the great presentation. I think we just get close to like 1 hour session. So probably if there is any burning question, we can I think we can take 1 or 2 questions for the interest of time. So please feel free to ask any questions. If not, then actually I have a very small short question, because I think this might be, I think this is a very interesting project, and I actually wonder the lifespan of the facility. So when we are making the investment, we have to think about how long commitments we need for this facility. So, and also, do we have to worry about the takedown cost? For instance, when we are talking about nuclear energy plants, it takes a lot of money for the takedown. So how about this facility for landfill gas to energy?
Yeah, great questions, Senki. So first of all, I'm going to address the first one. Is about sort of how long do they last. So landfills can go on for a very long time. Landfill gas generation can go on for a very long time. Even after the landfill has been closed, it can go on for 20, 25 years producing gas. So every million ton of waste approximately generates about 300 cubic feet per meter of methane gas. And it can go on for 20 to 25 years according to estimates. So that's why in our data set, about half of the landfills that have an LFGE are closed. They're not even open. They're already closed, but they have an LFGE project. So it can go on for a long time. And of course, when you calculate the net present value to look at the economic viability, you have to look at that as well. It's not the only factor. The composition of the waste is very, very important. Are we generating enough methane, and that's based on the organic content of it. It's based on moisture conditions as well. So the economic feasibility and all that stuff, excuse me, we'll take that into account. The second question is a very interesting one that I haven't thought a lot about, which is sort of the takedown of these installations. I'm quite sure it's not like nuclear. That's something else. But I'm sure there's a cost to it. The question is whether it can be repurposed for something else, and probably it can be. But I don't have sort of the numbers on the top of my head and to tell you what that cost would be. Yeah,
that's great. Thanks for answering my question. So, if there's no question from the audience, I think now it's a good time to finish our session for today. Again, thank you very much for joining us today, and I think we look forward to seeing you again in November Economic Outlook and Policy session webinar.
Thank you, everybody. Thank you, Senki and Dan, for hosting.
Thank you.